Once again, not once again, good afternoon, everyone. Okay, we are meeting first time in the afternoon. So now we will go ahead with our next session. This is based on tutorial. So in this tutorial, we are going to discuss about this thin film deposition, how you can make a thin film, first of all. What are the equipment currently which we have here? So on that you can see the facility and how we can make the thin film based on this chalcogenide based devices. And if we want to take their resistivity measurements, so how we can perform that thing. So on the basis of these things, just I will cover few aspects. So first part that will be the resistivity measurement of thin films, and then thin film deposition. So this I will discuss here, first part, and the second portion will be demonstrated in the laboratory. So we can identify in which way we can cover these aspects. So if we talk about this phase change memory, so again just have a quick recap. The thing probably we have witnessed so many times these things. What are the phase change material and the style line, and what are the principle of these phase change materials, set, reset, and all those things. So based on that, we need to understand how you can deposit this film. So there are multiple techniques are available. PVD's basic techniques, it is already there. No, some thermal evaporator based techniques, sputtering units, and so if you go some higher sides, so ALD deposition is also there, molecular pneumatics. So based on that you can coat these chalcogenides. Based on the appropriate composition, you can deposit these thin films, and then accordingly you can characterize. So for deposition of these films, based on the elements, you can identify the suitable composition, and then you can deposit. So I would say this is one of the important thing, because if we are not able to calibrate material properly, then how we can go further for device level characterization. Okay, so this is the very important aspect: material fabrication, material deposition. So in that level, you need to first identify the suitable technique, suitable deposition method. On the basis of that, we can see these things. Okay, so for this characteristic, for amorphous crystalline, all those this functionality, if you want to see these things, this performance, so you should have a samples. You should have a material. Then only you can identify this. And these are the elements. So these elements we need to prepare. Okay, so for that we have a suitable, appropriate technique. So as I talked about this multi-bit PCM technology, so you are knowing this, two phases are there. Based on that you can identify these, if you easily tune, then you can see this multi-bit state, all those things. So this is the material property actually, where you can tune this, where you can identify. And based on the number of levels, you can say that yes, this is the number of bits are available. Okay. So the overall thing is that this resistance, to identify the resistance of material is also very important. Although this is the programming curve, but initially how the material is performing, what is the resistance, contrast. So that is very, very important. So for that, you need a resistivity measure, identify the thin film. This is the prior and most important thing, is that to understand how the material contrasts. So after identifying a material, you know first you have to identify their resistance, contrast, and with the help of that measurement, you can also identify the crystallization temperature also. So as we know, this large resistance contrast allow multi-bit programming, so we need to identify large resistance contrast. So that we need to figure out with some kind of instrument. So this is one of my work actually, which is earlier reported for this resistance measurement setup, where we can identify these setup where we could calibrate or we can measurement the resistance of thin film to identify their resistivity. So as you can see here, it is kind of a tubular furnace, and where in between it's a kind of a tube where at the center of this setup, this your sample is placed. You can place your sample, and then it could the value of resistance can be directly measured into this computer. So what are the instrument it is used here? So this overall setup, it is connected with SMU, source measure unit. So this source measure unit, it is going to provide you the resistance value, okay, resistance value of your thin film. So how it will do? We will see this thing. So this is the electrical setup basically, and then along with that you have a switching network. So switching network is that it is having a special purpose for measurement of this thin film. So this is, it's a kind of a switching. It is switching the terminals, and then to automate this setup, you have here you can see this data acquisition system is also connected, and it is interfaced through computer. So the thing is that this computer is going to operate or going to automate by the help of this this DAC to make automate this switching network, and then appropriately this terminal you can change from here. Okay. So how this is, we will see in the subsequent slide, but just try to have an overview of how this thing is developed here. And then this whole thing is fully automated by computer, because you need to identify in situ measurement. You are heating the sample, and then simultaneously you are identifying the resistivity also. So this is the overall way by which we can see this. So what method actually it is identified here? So if you see the whole setup, the thin film of this material, it is identified using this Van der Pol method. So Van der Pol method is reported long back in 1958, as you can see by this Phillips research report in 1958. So they have proposed one method to identify a resistance of any non-uniform sample or any sheet, I would say. It is not a kind of a linear resistance where you simply apply voltage and simply get a current or resistance. It is not like that. It's a kind of a sheet. It may be uniform also, it may be non-uniform also. So that based on that you need to identify these things. So to get more idea about this method, you can refer this work. So it's a kind of they have proposed this mathematical relationship, where we can see this resistance of RA and RB. So this is kind of a different configuration in RA and RB. So RA is what? First you are sourcing this side and measuring this side, so you are getting one resistance, okay? And on another side, if you see, you are just changing the terminal of source and measurement, and then you are getting RB. So this RA and RB, yeah, that you can identify. And when you solve this equation, you can solve this equation using some mathematical tool and all. You can simply, if you are able to identify RA and RB, you can directly solve this equation for RS using MATLAB. Even you can solve mathematically also. And if you have the thickness of this material, so in that case you can see and you can identify the resistivity of this material. So it's a kind of a method by which we can see the resistance. But how they have proposed this? So to get more idea about this, you can refer this paper, and I can also give you brief idea about this, what is this method and how it works. So you can see here. So if we talk about this method, so based on this method, this mainly developed this method in this by this report to measure the resistivity of thin and flat sample of semiconductors. So if we have a thin film of any sample, so to identify their resistivity, as you can see. And the Van der Pau technique for resistivity measurement allow avoiding problem due to incorrect knowledge of sample geometry. So if you don't have any knowledge of any geometry, whether it is linear or what kind of sample is there, so you can simply place this contact at the edge, and you can do multiple measurement, and they have appropriate mathematical equation, and you can do this. So, but there are certain assumptions. So the assumption is that the contacts are on the edge of the sample. Okay, they have done some kind of assumption, and then the contacts are sufficiently small, and the surface of the sample is simply connected. It's a kind of some metallic contact, and it should be connected. So by which you can see. And based on that, this method, you can get this resistance value. Say suppose I am telling you are sourcing in this particular terminal. If this is your sample, and you have identified 4 contacts at the corner. Say suppose this is your sample, I would say, okay, and you have identified these 4 terminal. Say this is your thin film, or coated any film, whether it is through spin coater or thermal evaporator, or even for the sputtering unit. So you got any film or any size, and you can place such kind of contact. So if you are sourcing these 2 terminal, and you are getting bias on another side, so you can get this resistance kind of a V by I, this relationship, VPO by I. Okay, so this it's a kind of, so what is the thing basically here? So the thing is, first you need to identify the current density, and based on this mathematical equation, you can get the current density and the radial electrical effect. Okay, so after solving this equation, you can get proper understanding about the resistivity of, because ultimately it is the relation between current density and radial electric field, which is very, very important. Then if we know the potential drop due to this electric field, okay, and this is kind of a potential drop due to this electric field, if you are able to identify, and then if you are able to suitably properly, you can solve this mathematical equation to identify this relation with respect to this radial bias, I would say, because it is not simply voltage, it's a kind of you are calculating with respect to field and that radial change. And then after solving these equation, you can directly identify these resistance value with respect to this agent's identified contacts at the edge of the terminal. So this is mathematical equation. I am not going much inside into that, but you can refer this work where you will get more. They have solved everything with respect to their assumption. Our main focus is that how we can get the sheet resistance of any sample, which is very, very important, because our ultimate goal is that we are identifying any method and we are getting low. So it's a kind of some mathematical relation where you can get a potential drop due to current leaving at point, and then we can get the desired value of resistance with this mathematical expression. They have some logarithmic values here with respect to this bias and current. And then finally, if we will able to identify, so after solving equation 7 and 8, 7 and 8 means what? 7, if you see, this is R, M, N, O, P, and this is another is R, N, O, P, M. So what is this? It's a kind of they are changing the terminal of source and current, and then they are identifying this relation. So if you are able to solve this equation, so you will be able to identify this ρs value, this is kind of resistivity, and this will be helpful to identify the resistivity value. So this is a kind of a configuration which I was discussing about that. So where this Van der Pau resistivity method, so this is the 4 configuration, different configuration. So these two, where here you are sourcing, here you are measuring, here you are sourcing, here you are measuring. So these two more or less same. Why? Because it is identifying the reciprocity theorem. Okay, so this is after averaging out this value, you will get 1 RA, and if you average out these two values, you will get RB, and you put simply in this equation, and you can directly get the C2 distance value. Okay, so this is the way by which we can calculate the resistivity, and we can identify the method actually to get this value. So we were here. So this is the mathematical equation. So our main focus is that we are not going to do the research on that, but they have simply taken this value, and we can further identify that. So now here important thing is that how you can get these two values. How you can do this value. So have you earlier done this measurement? People who are working in this direction. Anybody? Have you earlier measured thin film resistance?
Yeah, we have.
So how you are?
Simply we took the 4 points on the thing, and then we source the current in different direction from A to B, then measure it from C to D. The voltage we measure from C to D. In the other case, we'll do the reverse part of that. So then we get two values of the resistance, RA and RB. Then we average that.
Average value.
Yeah.
Okay. So how you are changing the terminal? How you are changing the terminal? You are getting making two value, and then you are averaging.
Yeah.
So how you are getting that value?
We were getting 8 values of resistance. Yeah.
Yes.
So they were 1, 2, 3, 4, 2, 1, 3, 4 kind of combinations. Then we average that value out.
Okay.
Yeah.
Okay. So I'm curious to know. I would say how you are changing the source and sense terminal.
So it is like we keep the probes at same location. Only what we do, we change the directions.
Okay.
We have 4 manipulators. Yeah. Then we only change the direction of the current in the the source we supply. We only change the direction.
Only changing the direction.
Yeah.
Okay.
We have 4 SMUs.
4. Okay.
Yeah.
4 SMUs.
Yeah.
Okay. Understood. Now understood. So here, what we are doing here in this case, just we can use it. It's a kind of a switching matrix, low cost switching matrix. It is just provide us, simply you can use the relay, and you can control this with data equation, and this is the setup with, you can connect your one SMU, and it is provide us the, beauty so that you can change the terminal. So this is the thing. So here these connections are coming for your source and sense, and here for your sample it is going, and through this data equation, NI based data equation, you can control and you can get that. So this is it's a kind of a custom built switching network, and the data equation setup which is reported in this work, where you can see with respect to that SMU just to change the terminal and to identify the resistance value. So this is the pictorial view graph of this switching board, where this kind of a relay is there, and it is connected with transistors, so it is going to operate through this control signal, and based on the appropriate circuitry, you can easily provide your control here, and then you can see. You can source, I would say, the current here, and you can get desired voltage value after changing the different directions. So this is the circuit diagram of this switching network board. And then if we try to figure out the connection configuration, so it's a kind of 4 configuration. You can enhance this 4 into 8 also, the way we can get. So 4 values you can average out, and then remaining 4 you can average out, and then you can directly get this value. So here this method which we can use that, where 4 configurations are identified, where you can see how it is programmed. So for connection configuration 1, what are the relays are operated, as you can identify that, and what are the desired output you are getting. So based on that, you can operate this value, and you can see the resistance value, and then further you can average out the corresponding values, and then you can get value. So the thing is that here the status of your relay, basically, to get a particular connection. So this is the thing, and this is the program algorithm which is programmed through LabVIEW programming, where the whole thing is controlled to identify these values, where we can just apply a source current value and it is calculating the voltage, and then after it is providing the appropriate connection, then a further measure, and then again activating switching network. So as we are getting 4 configurations, so 4 type of measurements are there, and then finally we can get average resistance value of this. And after identifying this appropriate mathematical formula where you can directly get this value, seat resistance or value, after providing the value of RA and RB, as you can see here. So this is 4 values you are getting, so 2 similar value you can average out, and then you can get the particular resistance value, and you can use this value to get the seat resistance of your thin film. And if you have the thickness of your film, you can directly get the resistivity. So this is the way by which this instrument is working, and this is the overall setup, this front panel of that program, where we can see. So this is kind of a material, phase change material, which is showing the the resistivity change, resistance change, I would say, with respect to temperature. Okay, so the thing is that we can identify this resistance contrast first with this, okay, and another thing is that the crystallization temperature we can see with this. So using this measurement, you can directly calibrate your material first of all, because crystallization temperature is very important. So we can get the crystallization temperature with this, and you can also get the resistivity contrast for your chalcogenide based material. So this is the overall setup by which we can see the change in resistance value and the crystallization temperature. So this is the overall thing related to your temperature dependent resistivity measurement setup. And another topic just I will move. So this is the thin film deposition setup, so which we have in our lab. So this is the multi-target magnetron sputtering unit which we have in our lab. So just I will brief you here little bit about this setup, and then you can have a quick round on that. So the thin film which we can fabricate with this. So this setup is having basically RF source, and along with DC source also have, and the source number which is having, we have 2 sources. So on that you can provide, you can do a single element deposition also, and if you want to do a co-sputter deposition for phase change material, and after optimizing the power and the chamber inside the environment, I would say, and so that you can properly calibrate the system. So what are the important parameters here? First, power. How much power you are providing. Based on that, everything is dependent. Okay, if you want to get a more thickness, or if you want reduce the thickness, or if you want uniform, everything you need to calibrate first of all. Same material can deposit at 20 watt also, 40 watt also, but there is a difference. Okay, that we need to identify using structural characterization, material characterization of the thin film, and then based on that we can do. Another thing is that deposition rate. So this deposition rate, if we see, so how you can identify the deposition rate. So for deposition rate, what we can do, you can deposit this phase change material, and some advanced setup they have directly some kind of instrument inside, and they can directly calibrate you. But further also you can have some understanding about the thickness, or you can do reflectivity measurement, you can do some AFM, cross-section FECM, and then you can see how much the thickness you are getting with respect to your sample, and then you can calibrate. Then you can get the deposition rate. That same condition you need to fix. Multiple times you need to do this. Okay. Once you calibrated one material, this is the deposition rate, and then you do multiple time measurement with same condition. Same condition means what? The here it is not mentioned. You can see there the value of how much you are providing the argon first of all inside. What is the pressure? Chamber pressure is there. The chamber pressure also you need to calibrate. Everything is dependent on that. And if all parameter is constant, then only you will get a uniform deposition. Okay. Next is that rotation of substrate. So rotation of substrate is also very important. If you make the rotation very fast of your substrate, so you may get the change in the film quality and uniformity. You will get. So you need to optimize and appropriate substrate rotation so that it can be helpful to get the uniform thickness. Because when you have the confocal arrangement in your sputtering unit where it is kind of tilted with some angle and then rotation it is providing, I will show you. So in that case, the substrate rotation is very important to get a uniform film and uniform thickness. So this is the just I'm briefing you. So we can you can check the deposition also and some kind of plasma as well. So this is it's a kind of just view graph. Just we'll discuss about the principle how the sputter deposition works actually. So if we see this is the chamber. This is the chamber, and it's a kind of you can see your target is here, and from here you are providing the RF power. Okay, this is the RF power you are providing, and this is the chamber. So chamber, this is for vacuum, so you are continuously connected with some kind of a turbo pump or some vacuum pump, so that the whole particle can go out. You need to make chamber very clean, then only you will make the deposition. Okay, and then one side you are making the incident ions. So incident ions means argon we are purging from here. So what happens? The moment you are making, first you are creating a vacuum, then you are closing this, and then you are providing the RF power and you are purging ion. Sometimes you need to release this also if it is very dense inside organ is there. So what will happen? This argon atoms are getting hit, okay, on this target. When it's hit into this target, so the atom, this particular atom, this green one, it is getting out, okay, and it is going to stuck in your substrate. Okay, so this process, this is the inside, it is happening, and when this process is happening, here you can see some kind of a color. Okay, so that color called as a plasma. Okay, so that plasma, you can easily see this plasma, and that plasma is nothing but it's a kind of the particular your atoms it is showing that, and or another what you can say, it's a sputtered atoms which is going towards the anode, and it is providing us the thickness, or it provides us the thin film. Okay, so this is the way by which this sputter unit works. But after looking into this, it is not. You need to calibrate. First, lots of conditions are there. This argon pressure, RF power. Sometimes if you want reactive sputtering, so you have some another this inlet kind of thing where you can provide some nitrogen also. You can put nitrogen doped. You can, if you want some kind of oxygen, you can provide oxygen also inside the chamber, and then you can do some kind of a deposition based on these things. Okay, so this is the overall idea. So advantage of sputtering deposition is that it is a widely used PVD technique. So PVD technique is a wide term, physical vapor deposition. So there are techniques on that available on that. So it's a classification. So on that, this sputtering is coming into that. So its favorite industry like microelectronics, optics, material science for precision and versatility. So from sputtering onwards, industry are accepting yes, these films are uniform and some kind of and more advanced research for ALD and some kind of there. So where industries are more having confidence on the thin film deposition. So this is some key benefits of that. So some kind of a high purity films, precise thickness, and uniform coating, and this wide material compatibility, strong adhesion. So you can go through with that. this is it's a kind of a metallic property why we are using this. So possibly I will provide some notes on that, so you can go through with that what is the main important point behind this sputter deposition and all. Okay, so my this discussion part of here, just I will stop here, then I can take few questions. If you have some questions, then we'll move towards our laboratory, where we will see the real experimental setup, so that you can have more feeling, more understanding about that. So I can take one or two questions. We need to wind up there. Then we need to go there also in laboratory. If you have any questions. Yeah.
How you are making the targets of if you want
target? So for the target, we can do either we can make a powder, okay. Just we can take a powder particular this material, okay, and if sometime appropriate composition you can directly get, okay. So this is bit difficult method, and you need to make kind of a inside furnace and everything. You need to heat up, and some pellet and all you can create bigger. But this won't work actually. So you can directly purchase from vendors. You can just provide an appropriate composition. If you have do own research on target thing, you can do that. It's not different composition you need to make, and there is process. You need to make as per, say suppose in this sputtering you have 2-inch this cathode size. Somebody is having 3-inch. So based on the size you need to prepare. So accordingly, because if you need a precise control on stoichiometry, so you need to, there are vendors are there, so you can get that appropriate composition, and then you can do research on that. Yeah, backside. Anybody else? Any query? Any questions? Okay. So, if not, then rather we should move towards laboratory. So you just go there and just see the instrument, and possibly we'll try to show you the deposition also, deposition of any material, where you can see the plasma and just see the sputtering setup. What are the components are available, and how we can prepare a chalcogenide based thin film. Okay. Thank you. Okay. Let's move towards the lab.
Okay, good afternoon. So welcome to Nanoelectronics and Emerging Memory Lab. So I hope you should have a sound knowledge on there about sputtering and about 4-probe measurement. So before deposition, we have to prepare our samples. So we have to clean our samples. So many are using RC cleaning, Piranha cleaning. Okay. So all chemical cleanings are there. You might know. So here we are using whatever your samples like substrates, either glass substrate or silicon substrate. We are undergo like DI water cleaning, followed by acetone, propanol, and hot tube, and then argon purging. And after that, we have to keep our samples 24 hours with desiccator, and after that we proceed to deposition. Okay. So what to do? So I would like to brief about sputtering. So sputtering is a PVD technique, physical vapor deposition technique. So it's a industrially well established, low cost and easy to use. Okay, as compared to other chemical strategies. So what we are doing, basic steps involved in sputtering. Like first of all, we have to introduce inert gas, like here we are using argon. At a high voltage, when we bombarded our target material, so it ejects atom or molecules towards the substrate, because here we are using negative and positive polarity. So negative means cathode is connected to target material, while body is connected to anode. Okay, so this principle is behind that. So before to that, so first I have to familiarize all the these valves here. Here we are using vacuum valve. Here this is our rocking valve. Okay, actually this is our rocking pump, and there is a high vacuum pump known as turbo pump. Okay, so what happens actually, rotary pump brings us from low level to medium level vacuum, and after that from up to 10 to the minus 3. Okay, and after 10 to the minus 3 to 10 to the minus 6 we will achieve by turbo pump. Okay, so what happens, first we have to open the rocking valve. So it will bring us the vacuum level to a medium level, and after that we open the vacuum valve. So what is the use of vacuum valve? It isolates the low vacuum to high vacuum level, and then to get the 10 to the minus 6 level of vacuum, we have to wait, this system, we have to wait up to 4 hours, okay, and we achieve 10 to the minus 6 level of vacuum, then we have to go for the deposition, okay. So what to do? First we have to introduce our inert gas, argon, then we will go with a parameter, like what is your RF power, what will be your argon content, what will be the SSCM of argon, and if you are using post-sputtering, then what will be the nitrogen or oxygen level, okay, or and what will be the means at what pressure we have to deposit, okay. So we need all that parameters, then we move forward for deposition, okay. So actually due to time constraint we can't show from the beginning. Actually we have on our system prior to 4 hours. Now we can show you the deposition process, okay. So now we reached up to, खोल देगी थोड़ा ये देख लेते हैं, थोड़ा इतना है यार. Now it's almost 10 to the minus 6 millibar, okay. Now we introduce our argon, okay. So we have two power sources, this RF1 and RF2. We have one DC source as well, okay. So DC is used for conductive material, whereas non-conductive materials are coated by RF. So shall we start? We have two magnetron. So we have loaded with two magnetron here, okay. So for the superlattice kind of deposition, we are using two magnetron at the same time, okay. So what we do, like we are calibrated earlier, that much time required to grow that much of nanometer of thickness. Okay, so suppose we have to grow 2 nanometer of thickness, so we know the time, how much time required. Now you can see the plasma here. You can see the plasma.
We have put here two materials, one is GST and one is between is it almost nanometer level, like if you calibrate it plus minus 5. That's why we
As you said, we are using your left hand side GST and the right hand side SB2. Okay. Okay. So as you know, chemical deposition is crucial in many industries like architectural glass display, contain thin film, your solar cell contains thin film, your pouch panel contains thin film. So what else?
Can you control the rotation rate?
Here. We can control. Actually, this is the standard rotation per minute. RPM is like 20 RPM per minute. So here we have 20 RPM. So we can control this rotation.
We cannot show it here.
Sorry?
We cannot increase it.
No.
That is fixed.
And these are all MFC mass flow cylinders. Here mass flow cylinders. So here we can tune our gas flow rate. Okay. So like now it is coming argon. So we have to set to in argon. Okay. If you want to nitrogen to pass or oxygen to pass, so we have to set the nitrogen or oxygen. Okay. And here we have this sucker. So as we have two magnetron, simultaneously we don't require two. So like I have opened one. Now I have opened one. So that right hand shutter I don't need, so I close that shutter. Okay. So now this shutter is opening, so it hits the stop substrate. Anything?
So you were saying that deposition rate, how does it depend on the
Deposition rate.
how does it depend on the deposition rate?
Sorry. Deposition rate, na? Actually, we have calibrated our machines by XRL, by ellipsometry, by profilometry. Okay, so all these results relate our deposition rate. So like we achieved for GST, what is the deposition rate? It's sorry, 100 nanometer almost. Okay, so we know that our machines gives us that much of thickness within a certain time. We have optimized almost for all targets.
Every target it will be same.
No. For GST it is different. For other material it is different. For different material, optimization is there. You have to do optimization. Okay, we'll show you a sample. Okay. Now it is not possible to show you because it will take another 2 hours to stop. Actually, what happens? Like aeroplane takeoffs, now there is a sound like boom. So when we start our vacuum, high vacuum, it will हम बोल देते हैं कि just confirm for seat belt. Okay. Okay. Then हम चले जाते हैं ना, फिर उड़ के आते हैं फिर वही लैंड करने के टाइम. हाँ. तो ये तो machine takes almost 1.5 hours for off. Because we can't shut down two substrates, two targets, because our need, because we are going to deposit our superlattice structure, so superlattice needs two substrates at a time, one upon another.
1:1.
Yeah. People are using 3 magnetron also.
As sir have already discussed in the theory class, that there is also a technique called co-sputtering.
Yeah.
So in the technique like co-sputtering, there are two kinds of, one can be a chalcogenide, one can be another material. So what we do, we use the RF power source, both of the sources, we use the co-sputtering at a single time. Here, as you can see, as sir have said, that one shutter is closed, another is open. Here, both of the shutters are open, and this is doing the post-sputtering. And after the deposition done, we do another some techniques like annealing and another etching kind of techniques to get the exact.
And I wish to add here, you can do reactive sputtering also. Okay, so what you have to do, suppose you want to deposit your titanium nitrate. Okay, so you have titanium target only. So what to do, another nitrogen will have to pass. So you need to know what is the percentage of nitrogen. Okay, so what to do, argon have to pass. Okay, no need to discuss this MFC. So with another MFC you have to pass your nitrogen content with a ratio. Okay, you need to know from your literature. Okay, and you have to pass your nitrogen as per the literature. So you can achieve your reactive sputtering. Anything?
Anyone have any questions or something?
So we can move to this RP measurement setup.
So this is the RT measurement setup. As you can see the whole setup here. This is one kind of probe station that we have, and this is a SMU that we have, and there is a DMM we have. There is a DAC measurement system, and this is our dedicated PC to measure the resistance versus temperature of a particular sheet. That means the thin film that we have grown using a sputtering technique or any other PVD kind of techniques. So what we do, we put our thin film sheet into this probe station, and after that this is a 4 probe measurement system. There are 4 probes are there. So what we are doing, we are connecting all of the 4 probes into our machines. The 2 probes gonna be connected with your SMU, and another 2 probes gonna be connected with the DMM, and in between that we are using our custom designed PCB. This PCB is nothing but just using for a switching network, because we will be integrated all of the systems into our LabVIEW system using our NI DAC system. So what happens when, as sir have already discussed about the Van der Pau method, so we are exactly executing the Van der Pau method practically using this electrical measurement setup. And so what happens, using the 2 probes that we are giving our source current, and in the opposite 2 sides, suppose there is a thin film here, in these 2 sides we are sourcing using SMU, and in these 2 sides we are measuring using a DMM, the digital multimeters we have. So in this method we are sourcing and we are measuring, and then after that, as you have seen already in the theory part, that how we are measuring the sheet resistance that we are getting. So in this system, as far as the Van der Pau method is there, we are using multiple cases, as the cases also have been discussed by sir, that we are just switching the four probes. So exactly what we are doing here, using our switching network, and our this switching network is just switches each and every time. So it sources there, measures there, again it switches, it sources there, it measures there, again it's doing. So it after getting all of the measurements, then we are integrated inside our LabVIEW system, and we are getting all the data, we are averaging it, and after that we have our own script there using the Van der Pau method, and the final we are getting the sheet resistance that we desired. So in this case, what we are also doing, we are varying it using the temperature. So we are getting a constant measurement, like we are getting 2 or 3 measurements per minute. So using this temperature control unit, we are giving temperature into this setup, and as the time goes, the temperature gets increased, and after certain time it gets increased, and we are measuring each and every iteration or each and every type. And what happens, as we have grown after it's in the amorphous stage. The sheet is first in the amorphous stage, but as we are increasing the temperature, we know that thin film will go from the amorphous to the crystalline phase at a certain temperature. So that is what we are trying to measure using this 4-proof measurement system. So using this unit, we can go above 500 degrees centigrade. But we are till now getting almost 400 to 450 degrees centigrade. So in this, almost all the materials that we grown, we are getting our amorphous to crystalline phase, and we can see inside this is our front panel of our LabVIEW measurement system. And in this measurement system, as you can see, that the sheet resistance has been measured with respect to time, and also we are measuring it with respect to temperature also. So to get the temperature, what we are exactly doing, we can get the temperature directly from the temperature controller unit, but it will vary from the actual temperature that the sheet is getting. So for this reason, by using this stand, we are connecting a thermocouple on the tip of the sheet, and we are integrating it again using this NI DAC into our LabVIEW measurement system, and we are getting the temperature versus resistance versus temperature graph for a particular.
Can I see your the tip of your
thermocouple? Yeah, you can see that. So this is our a probe that we have. This is a tip. This tip is typically made of tungsten tip, and it's very sharp. just to get the touch just above the sheet so that we can get the touch. So this is the tip that we are doing, and we are getting the measurement using this wire, and we are connecting into the SMUs or the DMMs, desired DMMs that we need. So thank you so much for this.
We combine it. We use the sealing we select.
The topic of our course. So in this lab, what we are doing, just I'll brief you, then you can continue with the discussion with the particular setup. So what we are doing, we are fabricating or deposition of that material. Memory application, that is well known, we are doing that. So using this sputter deposition, we are making these different alloys which you have gone through in the last few days, starting from GST, starting from AIST, and then GT, all those kind of material. Okay, so we are optimizing appropriate condition here, the way I have discussed with you, and then we are making the implements. So the thing is that this setup, it could be it can be used for multiple material also other than fashion, metallic also you can use, some metals also you can coat. And if you do some more rigorous analysis to optimize any material, so you can do multiple elements, you can you can provide a different power and chamber environment, and you can prepare your stoichiometry also. The way, for example, I am telling you, we had so many times GSBT 225, so germanium is 2, SB2, T5, so this is stoichiometry. So you know, some advanced setups are there where 3 cathodes inside, 3 cathodes. In one you can place germanium, in one you can place antimony, in tellurium, and you can adjust power of each. So GST, germanium, antimony, telluride. So what is rich? What is more? Tellurium. So it means tellurium you need to provide more. So in which way? You can either provide more power to them, other less. Okay. So that tellurium content will be more. So it's a part of co-sputtering. So you can read more about the co-sputtering method by which you can prepare this stoichiometry of chalcogenide based material and then appropriate parameters the way you can see here. This is the MFC by which you can mass flow controller of different gases. You can provide that and you can control the chamber environment. Okay. And similarly, it is having inside some heating element also. So if you want to make your deposition with some kind of a temperature, that also you can do. So in simple word, I would say this is very, very important part. As per this lab also and as far as our research concerned. Without material we cannot do anything, without device. Okay. Then later on we are fabricating this and we are preparing some sort of prototype device and then array, and then we can take further for electrical side, some characterization, some kind of, that array which I have shown you, phase change array was there, one was set, another was reset. So this is our long-term goal actually. I am not telling that we have reached that level, but it's a long-term goal by which we can prepare that and we can take some advanced application for, some multi-bit data storage or some this AI application and all. So it will take some time. Okay. So here you just visualize this setup. This is a standard PVD technique. No, this is PVD. This is the part of PVD technique. Probably who are taking VLSI course, microelectronic course, and who are doing semiconductor research, PVD technique is one of the very important and basic instruments. Okay, by which you can prepare your materials, silicon out there, and these materials and all metals, everything you can coat and you can prepare. So as far as people who are having more interest, interest on semiconductor kind of research, they should get more idea about this. If you are telling that you are knowing about this setup, people will be, okay, yes, at least you are knowing a little bit about that. Okay, so this is if you go any fab lab and all, so you will identify such instruments. So at least we don't have fab, but at least we have some facility by which we can calibrate this. Okay, so try to see this setup. There are multiple parts, and you can just see the thin films also, which we have drawn earlier here. You can see, you can check how the thin films are there. And along with this, the parts. So as I told you, we can do co-sputter, two materials. So for that we have two different power source. Two different source means you need to provide two power. So these power source are there. So this is power source, you can say. This is not local actually, because you need to provide appropriate power. So precise power should be there. Then only you can get uniform layer. So this is serine based power supply we have brought, and we have integrated in this chamber. So we are working currently on this optimization of different material along with some multi-layer formation and all to identify this chalcogenide based nano devices. Okay, so this is more or less related with this sputtering unit, and probably you can see the plasma also. In which way? We can show them just two source and then deposition and how it works actually. And along with that, you can see that thin film resistivity measurement setup which I discussed with you. So there the things are there. So how it is integrated, so you can have a look on that setup also, and try to discuss more. Try to this session is specifically it is for interactive. This is for so that you people can be aware about that. Tutorial का मतलब यही है. So we should understand the fundamental. Discuss, try to get the more idea about this setup. And if you have any doubt, just let me know. Okay? Yeah, thank you. So if any doubt is there, just let me know. अभी आप लोग just interact करिए, देखिए setup के बारे में, and then whenever we will get time, so we can discuss. Okay, so tomorrow we have an exam also, after say second half. So prepare for that, whatever we have gone through these days. Grades अभी मिलेगा. Okay. What's your comment?